Reality is not what it seems. The universe is woven from a quantum fabric of space-time, a hidden layer where the rules of common sense break down. Albert Einstein himself called reality a persistent illusion. This video will pull back the curtain on that illusion, showing you how the bizarre quantum world connects to the vast cosmos to create everything we see. By the end, you will understand the universe in a fundamentally new way, grasping concepts that explain black holes, the Big Bang, and the nature of existence itself. How can a single particle be in two places at once, and what does that mean for the flow of time? The answers lie within the quantum weave, a realm where nothing is solid and everything is connected. What part of this hidden reality are you most curious to explore? Isaac Newton saw the universe as a perfect, predictable clockwork. An apple falls, and the moon orbits, both guided by an invisible force of gravity acting instantly across vast distances. This view held for centuries, a masterpiece of order, but then came Albert Einstein, who saw the cosmic stage not as rigid and absolute, but as something soft and malleable. He asked a simple, profound question. What if you were in a falling elevator and you dropped a hammer? To you, it would seem to float weightless. There would be no way to tell if you were in free fall toward Earth or simply drifting in the empty, force-free depths of space. From this elegant thought experiment, a new vision of reality was born. Einstein realized gravity is not a mysterious force pulling at a distance. Instead, it is the geometry of the universe itself. He fused the concepts of space and time into a single entity, space-time, a four-dimensional fabric. Think of space-time as a vast, taut rubber sheet. Place a heavy object like a star upon it, and the sheet curves, forming a deep well. A smaller object like a planet simply follows the curve of this indentation, trapped in an orbital path. This was Einstein's general theory of relativity. It was a complete reinvention of gravity. Where Newton saw a force, Einstein saw a landscape. This new framework was so powerful that its own equations predicted the existence of places where the fabric of space-time curves into an infinitely deep pit, a black hole, long before any telescope could confirm it. Yet for all its brilliance, Einstein's cosmic fabric was smooth. It described the grand stage of the universe, but it said nothing about the frantic, chaotic actors upon it, the tiny particles governed by the wild rules of quantum mechanics. So we are left with a beautiful but incomplete picture. What if Newton's falling apple was not just bending space-time, but was also a blur of quantum probability, existing in multiple places at once until it hit the ground? To answer that, we had to peer into the heart of the atom itself. That smooth cosmic stage Einstein described was about to be shaken by a discovery from the subatomic world. Picture a single photon of light flying toward a barrier with two thin slits cut into it. Common sense says it should go through one slit or the other, like a tiny bullet. But it does not. Instead, it behaves as if it is a wave, passing through both slits at once and creating an interference pattern of light and dark bands on the screen behind it. This is the particle-wave duality, a paradox that lies at the very heart of quantum mechanics. The pioneers of this new science, like Niels Bohr and Louis de Broglie, realized this was not just a trick of light. They proposed that all matter, from photons to electrons to you and me, possesses these wave-like properties. The solid world we experience is at its core a symphony of probabilities. Bohr himself admitted that anyone who is not shocked by quantum theory has not understood it. This fundamental strangeness directly challenges Einstein's smooth space-time. If the particles that make up the universe do not have definite positions until the moment they are measured, what does that say about the stage they perform on? It implies that space-time itself might not be a continuous fabric. but something far more fuzzy and uncertain. An electron does not orbit a nucleus like a planet around a star. It exists as a cloud of possible locations, a probability wave defining where it might be found. This blurriness at the tiniest scales forces us to ask a profound question. If the actors on the cosmic stage are fundamentally probabilistic, how can the stage itself remain rigid and deterministic? The search for an answer would lead physicists toward an even deeper mystery, the quest to quantize gravity itself. This inherent blurriness of the quantum world has a name and a profound consequence. Werner Heisenberg, in 1927, unveiled a principle that shattered any remaining classical illusions. The uncertainty principle states a fundamental limit to what we can know. You cannot simultaneously pin down the exact location and the exact momentum of a subatomic particle. The very act of measuring one property inevitably disturbs the other. It is not a limitation of our tools, but a fundamental feature of reality itself. The particle does not possess a definite position and speed waiting to be discovered. It exists in a state of inherent fuzziness. This quantum uncertainty is not confined to particles in an experiment. It permeates the entire cosmos, even in what we call empty space. The vacuum of space is not truly empty. It is a seething, bubbling sea of quantum fluctuations. Pairs of virtual particles, one of matter and one of antimatter, spontaneously pop into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and returning the energy. They are a direct result of Heisenberg's principle, a temporary loan against the cosmic ledger of energy and time. The physicist John Wheeler took this idea and applied it to the fabric of the universe. He proposed that at the tiniest imaginable scales, far smaller than an atom, space-time itself is not smooth. It becomes a chaotic foam, a churning ocean of fluctuations where tiny wormholes and baby universes might continuously form and dissolve. This quantum foam is the ultimate texture of reality, a realm where the very concepts of here and there, before and after, lose their meaning. This fundamental fuzziness has dramatic implications for the most extreme objects in the universe. Take the heart of a black hole, the singularity. General relativity predicts a point of infinite density where space-time curves to a sharp, mathematical point. But quantum mechanics, with its inherent uncertainty, suggests nature abhors such infinities. The same quantum fluctuations that define the vacuum could act as a kind of pressure, preventing matter from collapsing into an infinitely small point. The singularity may be replaced by a fuzzy, dynamic core, a Planck star or a bounce, where the laws of physics remain intact. Similarly, these vacuum fluctuations are thought to be the very seeds from which the entire cosmic structure grew. Tiny, random variations in the early universe, magnified by a period of rapid inflation, became the blueprints for galaxies, stars, and ultimately, us. Every structure we see in the night sky can be traced back to these quantum tremors. So when a virtual particle pair appears, it does not just exist in empty space. For its fleeting lifetime, it possesses energy, and energy warps the fabric of space-time according to Einstein's own equations. Empty space is therefore alive with microscopic, fleeting gravitational fields, a constant simmer of geometric change. This raises a monumental question. If the actors are quantum and probabilistic, and the stage itself is made of the same stuff, then how can we possibly describe the force of gravity, the curvature of that stage, using the classical, smooth language of Einstein? The search for a theory that can answer this, a theory of quantum gravity, becomes the greatest unsolved puzzle in modern physics. Einstein was deeply troubled by a bizarre prediction of his own quantum theory. He called it spooky action at a distance. Imagine creating two electrons so deeply linked that they become a single quantum entity, even if you separate them to opposite ends of the galaxy. Measure the spin of one, and the other instantly snaps into a corresponding state. This is quantum entanglement. It defies the cosmic speed limit Einstein himself established, the speed of light. Information seems to leap across the void with no travel time at all. For Einstein, this was proof that quantum mechanics was an incomplete description of reality. He, along with colleagues Podolsky and Rosen, crafted a famous paradox to expose this absurdity, arguing there must be some hidden variables, some deeper layer of reality that determines the particle's fates from the start. For decades, this was a philosophical debate. Then came the experiments. Physicists like Anton Zeilinger began testing entangled photons over distances of kilometers. The results were unequivocal. The spooky action was real. There were no hidden variables. The universe at its core is fundamentally non-local. This has a staggering implication for our cosmic stage. Entanglement challenges the very idea that points in space-time are truly separate. Two particles can be light years apart, yet they act as one unified system. How is this possible unless the space between them is, in some sense, an illusion? This deep interconnectedness suggests that the smooth, continuous space-time we perceive is not the final layer of reality. It might be a projection, a hologram emerging from a vast, underlying network of entangled quantum bits. Think of the universe as a cosmic tapestry. From a distance, it looks like a smooth, continuous image. But up close, you see it is woven from countless individual threads. Entanglement could be the weave that connects those threads. Some physicists now speculate that space-time itself is knitted together by these quantum connections. The gravitational force that holds galaxies together, the curvature that guides planets, might all be a consequence of this immense, invisible web of entanglement. So the next time you look up at the stars, consider this spooky possibility. The vast emptiness between them may not be empty at all, but thrumming with quantum links, a hidden architecture that binds the cosmos into a single, inseparable whole. If entanglement weaves the fabric of space, then what role does the force of gravity play in this grand tapestry? This cosmic tapestry woven from entanglement holds a deep and troubling secret, a flaw in its very foundation known as the Vacuum Catastrophe. We have already seen that empty space is not truly empty, but a seething sea of quantum fluctuations where particle pairs blink in and out of existence. Each of these fleeting events carries a tiny amount of energy. Quantum field theory, our most successful framework for describing particles and forces, allows us to calculate the total energy of this vacuum. The result is a number so catastrophically large it defies comprehension. This vacuum energy should, according to Einstein's equations, generate a powerful repulsive gravity, a cosmic force pushing everything apart. The strength of this push should be so immense that it would have ripped the universe apart in the first moments after the Big Bang, preventing any star, galaxy, or planet from ever forming. Yet when we look out at the cosmos, we measure the actual effect of this vacuum energy. It is there, driving the observed acceleration of the universe's expansion, but its value is almost zero. Not just small, but 120 orders of magnitude smaller than the theoretical prediction. That is a 1 with 120 zeros after it. It is the worst mismatch between theory and observation in the entire history of science. Why does the universe seem to ignore almost all of this vacuum energy? Why is the gravitational pull of this seething quantum sea so inexplicably feeble? This is not just a minor puzzle. It is a screaming contradiction that points to a fundamental gap in our understanding. Cosmologists like Sean Carroll describe it as the most embarrassing problem in theoretical physics. We have two pillars of modern physics, quantum field theory and general relativity, and when we try to combine them on this one specific point, they produce a result that is spectacularly, undeniably wrong. This vacuum catastrophe forces us to consider that our theories are missing something profound. Perhaps unknown particles, predicted by theories like supersymmetry, could cancel out vast portions of this vacuum energy, leaving behind the tiny residue we observe. Or maybe the universe has more dimensions than the three of space and one of time we experience, and the gravity generated by the vacuum energy is leaking into these hidden realms, diluting its effect in our own. Another possibility is even more radical. What if our very concept of vacuum energy is flawed? What if, in a complete theory of quantum gravity, the energy of the vacuum simply does not gravitate in the way our current, incomplete models suggest? The vacuum catastrophe is more than a calculation error. It is a direct message from the universe telling us that the quantum fabric of space-time has layers we have not yet begun to perceive. To solve it, we must find the thread that truly weaves quantum uncertainty with the force of gravity, finally uniting the actors with the stage. Gravity feels so immediate, so powerful when you trip and fall. Yet on the cosmic scale, it is the weakest force by an almost unimaginable margin. A simple fridge magnet, a tiny sliver of metal charged with electromagnetic force, can defy the gravitational pull of our entire planet, lifting a paperclip toward the sky. This is the hierarchy problem, a mystery that asks why gravity is so incredibly feeble compared to the other fundamental forces. The strong nuclear force that binds atomic nuclei is 100 times stronger than electromagnetism. And gravity is weaker than that by a factor of 1,000 trillion. The numbers are so vast they lose all meaning. This is not a minor detail. It is a screaming anomaly in the laws of physics, a clue that our understanding of space-time is missing a fundamental piece. For decades, physicists have grappled with a simple question. Why is gravity the cosmic wallflower, so weak it seems to barely participate in the dance of the quantum world? One compelling idea, championed by theorists like Lisa Randall, suggests that gravity is not inherently weak. Instead, its strength is being diluted, leaking away from our perception. Imagine our universe of three spatial dimensions as a vast, three-dimensional membrane or brain, floating within a higher dimensional space called the bulk. All the particles and forces we know, like electrons and photons, might be stuck to our brain like waves on the surface of the ocean. But gravity, the curvature of space-time itself, could be different. The hypothetical particle that carries the gravitational force, the graviton, might be the only thing that can travel freely through the full volume of this higher dimensional space. If gravity is spreading out into these extra dimensions, its influence in our familiar three-dimensional world would be spread thin, appearing incredibly weak to us. It would be like listening to a sound in an open field. The sound waves dissipate in all directions, growing faint. But if you were inside a narrow pipe, the sound would be concentrated and loud. In this view, we are living in the open field for gravity, but inside the pipe for every other force. This idea directly reshapes our image of the quantum fabric. Space-time is not just a simple four-dimensional sheet. It could be a complex, higher-dimensional geometry with hidden folds and membranes. The very structure of this fabric would then determine the apparent strength of the forces we experience. String theory, a leading candidate for a theory of everything, naturally incorporates these extra dimensions. In its framework, the strings that represent gravitons are closed loops, able to wander off our brain, while the strings for other particles are open, with their ends pinned to our membrane universe. The hierarchy problem forces us to confront the quantum geometry of reality itself. Gravity's profound weakness may not be a flaw in the laws of physics, but a profound message about the true shape of the cosmos. It hints that the stage upon which we stand is far grander and more intricate than we ever imagined, with hidden rooms and corridors we are only beginning to sense. If gravity is whispering its secrets from other dimensions, How do we even begin to listen? Einstein once called the cosmological constant his biggest blunder, but the universe seems to have had the last laugh. He originally inserted this number into his equations to force a static, unchanging cosmos, a notion he later discarded when the universe was found to be expanding. Yet decades later, astronomers discovered the expansion is not slowing down. It is speeding up, driven by a mysterious repulsive force we now call dark energy. And the simplest mathematical description for that force is, incredibly, Einstein's own cosmological constant. It represents the energy density of the vacuum of space itself, the energy of those quantum fluctuations we just discussed. But here lies the greatest numerical catastrophe in all of science. When physicists calculate what this energy should be based on quantum theory, the number they get is astronomically huge. The observed value, the one driving the cosmic acceleration, is almost zero. The predicted value is larger by a factor of 1 followed by 120 zeros. This is not a small error. It is like predicting the ocean should boil the entire planet, while in reality, we observe a single, quiet dewdrop. How can our two most powerful theories, quantum mechanics and general relativity, be so spectacularly wrong when asked to agree on this one number? This is the cosmological constant problem, a screaming paradox at the heart of modern physics. Experts like Steven Weinberg wrestled with this, even suggesting a startling possibility. Perhaps the constant is not determined by a fundamental law, but is a random, environmental variable. In a vast multiverse where countless universes bubble into existence with different values of the cosmological constant, we simply find ourselves in one of the rare, habitable patches where the number is small enough to allow galaxies and life to form. In most other universes, a stronger repulsive force would have ripped space-time apart before the first star could ever ignite. This anthropic reasoning is controversial, as it feels like giving up on a deeper explanation. Others seek answers by modifying our understanding of gravity itself, proposing new theories where the vacuum energy naturally cancels out or becomes irrelevant on large scales. The fate of the cosmos hinges on this delicate balance. Will the acceleration continue forever, leading to a cold, dark, and empty end? Or could the constant change, reversing the expansion into a future collapse? The cosmological constant problem is more than a calculation. It is a direct challenge. It tells us that our map of reality is still missing its most crucial feature, the one that connects the frantic quantum world to the vast, accelerating cosmos. This relentless acceleration of the cosmos, driven by a force we cannot fully explain, forces us to confront the nature of time itself. We experience time as a relentless, one-way flow, an arrow that never reverses. Yet physics tells a more complicated story. In Einstein's relativity, time is not absolute. It is a dimension woven together with space, and it can stretch and slow. A clock ticks more slowly near a massive object like a black hole than it does out in the emptiness of space. This is not a mechanical error, it is a property of the cosmic fabric. But what is time, really? The physicist Carlo Rovelli provocatively suggests that time, as we perceive it, is an illusion. Our brains create a narrative of past, present, and future from a reality where, at the most fundamental level, those distinctions may not exist. At the quantum scale, the equations are often timeless, describing possibilities and relationships without a preferred direction. So where does the arrow of time come from? The most compelling clue may lie in the concept of entropy, the measure of disorder in a system. The universe as a whole has been moving from a state of low entropy, a highly ordered beginning at the Big Bang, toward a state of ever-increasing disorder. We remember the past and not the future because the past was more ordered. A shattered glass does not reassemble itself because that would mean a decrease in entropy, going against the universe's overwhelming statistical trend. This thermodynamic arrow gives our lives their narrative direction, but some physicists propose an even deeper origin for time, suggesting it emerges from the quantum world itself. Could time be a product of quantum entanglement? In this view, the very act of particles becoming entangled and their correlations evolving could be what gives rise to our perception of a flowing time. The more entangled a system becomes, the more strongly time emerges as a property. This would mean that the interconnectedness of everything, that spooky action at a distance, is not just weaving the fabric of space, but is also responsible for generating the flow of time. This radical idea is central to some approaches to quantum gravity, like loop quantum gravity. This theory proposes that space-time is not a smooth continuum. Instead, it is woven from tiny, discrete loops, a fabric of finite threads. In this picture, time itself is granular. It is not a continuous flow, but a series of incredibly tiny steps, like the individual frames of a cosmic film. These are the atoms of time, the Planck time, a unit so brief that a second contains more of them than there have been seconds since the Big Bang. If this is true, then in the first moments of the universe, when everything was compressed into an unimaginably dense state, the nature of time would have been profoundly different. The discrete, quantum nature of space-time would have dominated, potentially replacing the singular Big Bang with a big bounce from a previous cosmic phase. The relentless forward march we feel may be the large-scale echo of countless microscopic quantum transitions. So the next time you glance at a clock, consider the depth of the mystery you are observing. That ticking is not just measuring hours, but maybe tracing the emergent rhythm of a quantum universe, a fundamental pulse underlying the illusion of a continuous flow. Perhaps the ultimate test for our understanding of space-time lies at the edge of a black hole. Here, gravity is so intense that nothing, not even light, can escape its pull. According to Einstein's general relativity, if you were to fall into a black hole, you would cross the event horizon and be inevitably crushed into the singularity, your information, the unique arrangement of particles that made you, lost forever to the universe. This is a clean, if terrifying, classical story, but quantum mechanics tells a very different tale. Its most sacred principle is that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased from the cosmic ledger. So what happens to the information of a book or a star that falls into a black hole? Does the universe simply forget? This is the information paradox, a direct clash between our two most fundamental theories of reality. The crisis deepened with Stephen Hawking's revolutionary work. He realized that the intense gravity at a black hole's event horizon could coax virtual particle pairs from the quantum foam. Sometimes one particle falls in while the other escapes, carrying away a tiny bit of the black hole's energy. This Hawking radiation causes the black hole to slowly, over eons, evaporate. But here is the catch. The radiation that escapes appears to be completely random, bearing no imprint of what fell in. If the black hole vanishes entirely, the information it swallowed seems to have been erased from existence, violating a core tenet of quantum law. For decades, this was an intellectual stalemate. How can both theories be correct when they make mutually exclusive predictions? The resolution may be as strange as the paradox itself. Physicists like Leonard Susskind proposed a truly radical idea, the holographic principle. Imagine a hologram where a three-dimensional image is encoded on a flat, two-dimensional surface. Susskind and others suggest that a black hole works in a similar way. All the information about everything that falls into it is not lost inside, but is instead perfectly preserved and encoded on its two-dimensional event horizon, the surface that marks the point of no return. The three-dimensional interior we picture is, in this view, a projection from that encoded data on the boundary. This is not just a clever trick for black holes. The principle suggests that our entire universe, with its three spatial dimensions, might itself be a holographic projection from a two-dimensional surface at the cosmic horizon. The solidity of the world around you, the depth of space, the very feeling of volume, all of it could be an emergent illusion from a vast, complex quantum system operating on a lower dimensional screen. This means a black hole is not a simple pit of destruction. It is an incredibly dense, complex quantum computer, furiously processing and storing information at the absolute limit allowed by physics. The paradox forces us to accept that the fabric of space-time is not fundamental. It is a derivative, a consequence of deeper quantum interactions and information exchange. So the next time you hold an object in your hand, consider the profound implication of its existence. Its apparent three-dimensional form might be the ultimate illusion, a holographic whisper emerging from the invisible, two-dimensional weave of reality's deepest layer. The solid world you touch might be the most convincing illusion of all. Gerard T. Hooft and Leonard Susskind proposed a principle so radical it redefines the nature of reality itself. The holographic principle suggests that our universe, with its rich three dimensions of space, is not fundamental. Instead, it is a projection, a hologram emerging from a vast, two-dimensional surface at the cosmic horizon. All the information needed to describe every star, every planet, and every one of us is encoded on this distant boundary, like a three-dimensional movie being played from a flat, two-dimensional disk. This idea did not come from pure speculation. It grew from the fiery logic of black hole thermodynamics. When a black hole swallows matter, the information does not vanish. According to the principle, it is perfectly encoded on the black hole's event horizon, the point of no return. The three-dimensional volume inside the black hole is a projection of that data. This elegantly resolves the information paradox, preserving quantum law while respecting gravity's power. The implications stretch far beyond black holes. Some cosmological models suggest our entire cosmos is a vast hologram. The force of gravity, which seems so intrinsic to the space we move through, may not be a fundamental force at all in this view. It could be an emergent phenomenon, a consequence of the complex quantum interactions happening on that lower dimensional surface. This provides a stunningly simple description of gravity, weaving it seamlessly into the quantum world. How can such a thing be possible? A powerful hint comes from string theory in the form of the AD/S/CFT correspondence. This is a concrete mathematical duality that demonstrates a direct equivalence. It shows that a gravitational theory operating in a hypothetical, warped five-dimensional space is perfectly equivalent to a quantum field theory, a description of particles and forces operating on its four-dimensional boundary. One side describes gravity and curved space-time, the other describes quantum particles without gravity, and they are two different languages for the same underlying reality. This is not just a philosophical idea, it is a working mathematical framework. So what does this mean for your daily experience? The depth of a canyon, the vastness of the sky, the feeling of a breeze against your skin, all of it could be a magnificent computation. Your consciousness might be experiencing a breathtakingly realistic simulation generated by entangled quantum bits on a cosmic screen we can never see. This forces us to confront the ultimate texture of existence. If space-time is a projection, then it must be pixelated. The smooth continuum Einstein described gives way to a reality built from discrete, finite units, the fundamental grains of space and time. Could it be that the universe is not a continuous fabric, but a tapestry of unimaginably tiny threads, weaving the hologram of everything we know? The holographic universe suggests space-time is a projection, but what is the projector? Another profound theory gives us a radically different yet equally compelling answer. Space-time is not a smooth, continuous sheet, but a fabric woven from individual threads. This is loop quantum gravity, a theory that dares to describe the universe in terms of discrete, finite pieces. Think of a finely woven sweater. From a distance, the material appears perfectly smooth and continuous. But if you bring it close to your eyes, you see the truth, a network of interconnected loops of yarn. Loop quantum gravity proposes that space itself is like that, a tapestry of unimaginably tiny, one-dimensional loops. These loops are not within space, they are space. Their connections and weaves literally define the geometry of the universe. Theorists like Carlo Rovelli and Lee Smolin developed this approach by applying the rules of quantum mechanics directly to the fabric of space-time. Where other theories struggle with infinities, like the infinitely dense point at the center of a black hole, loop quantum gravity sidesteps the problem entirely. It declares that space cannot be divided forever. There is a smallest possible volume, an atom of space. You cannot have half a quantum of area or a third of a quantum of volume. The universe, in this view, is fundamentally pixelated. This granular nature extends to time itself. Time does not flow like a river, but ticks forward in the tiniest possible increments, known as Planck time. This is the universe's ultimate frame rate, a rhythm so fast that in a single second, more of these moments pass than there have been seconds since the Big Bang. This discrete structure leads to one of the theory's most breathtaking predictions. What if the Big Bang was not the beginning, but a transition? In loop quantum gravity, the immense density of the primordial universe would have been met with a powerful repulsive force generated by the quantum geometry itself. Instead of exploding from an infinitely hot, infinitely dense point, our cosmos could have rebounded from the collapse of a previous universe. This is the Big Bounce, a cyclical vision of cosmic death and rebirth. The same physics transforms our understanding of black holes. The terrifying singularity, a point of infinite density predicted by Einstein's equations, is replaced by a Planck star, a region of fantastically high but finite density. Matter falling into a black hole would not be crushed into nothingness, but would meet this ultra-dense core and potentially be funneled elsewhere. This granular perspective on reality is not just mathematical poetry, it is a theory that makes testable predictions. The finite grain of space-time could subtly affect the travel of light across the universe. A high-energy photon from a gamma-ray burst, having traveled for billions of years, might arrive at our telescopes a fraction of a second later than its lower-energy companions, its journey slightly scrambled by the fine texture of space. Finding such a signal would be like feeling the individual threads of the cosmic tapestry, a direct touch of reality's deepest layer. The granular tapestry of loop quantum gravity is not the only vision of reality's deepest layer. Another idea, even more ambitious, proposes that the fundamental threads of the universe are not loops of space, but tiny, vibrating strings. This is string theory, a breathtaking attempt to weave all of nature's forces and particles into a single, elegant fabric. Forget the idea of a point like electron. In string theory, every fundamental particle is a minuscule, oscillating filament of energy. A string is so small that if an atom were the size of our solar system, the string would be no larger than a tree on Earth. The music of these strings creates the physical world. Just as a single violin string can vibrate at different frequencies to produce every note in a scale, a single fundamental string can vibrate in an infinite number of ways. One specific resonance might correspond to an electron, another to a quark, and yet another to the particle of light, the photon. In this symphony of strings, every force and every particle is a different note in a cosmic composition. The most profound note in this symphony is the one that describes gravity itself. String theory naturally produces a particle with the exact properties of the graviton, the hypothetical carrier of the gravitational force. For the first time, a single framework describes the quantum actors and the gravitational stage they perform on, offering a genuine path toward unification. But this beautiful idea comes with a staggering requirement. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions and 1 time dimension we experience. It demands extra dimensions, perhaps 6 or 7 of them, all curled up into a space so infinitesimally small that they are hidden from our view. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself to the size of an ant and crawl onto its surface, you would discover a second dimension, curled into a tiny circle around the hose's circumference. Our entire universe could be like that, with extra, compact dimensions woven into the fabric of every single point in space. This idea of hidden dimensions provides a powerful new perspective on gravity's profound weakness. Experts like Brian Greene explain that while the particles of matter and the other forces, like electromagnetism, are open strings whose ends are pinned to a 3-dimensional membrane, or brain, within this higher dimensional space, the graviton is a closed loop of string. This closed string is not stuck to our brain. It can wander freely into the full volume of the higher dimensional bulk, its gravitational influence diluted across many dimensions. To us, living on our 3-dimensional slice of reality, gravity appears incredibly faint, while all other forces confined to our membrane seem strong and immediate. We are essentially living in a cosmic brain world, a vast island floating in a higher dimensional sea. This vision pushes the boundaries of what we call reality. If true, it means that every event in our world, from a falling leaf to the orbit of a planet, is just a shadow of richer, more complex interactions playing out in a realm with more dimensions than we can perceive. The search for evidence is the next great challenge. Could the Large Hadron Collider create a microscopic black hole, a telltale sign of these extra dimensions? Or might we detect gravitons leaking away from our brain? The answers are hidden in the vibrations of the smallest things in existence, the strings that may be weaving the very fabric of our reality. These vibrating strings and hidden dimensions present a cosmic symphony, yet they leave a haunting question about the conductor. Who or what decides which note is played? At the heart of quantum mechanics lies a profound and unsettling mystery, the measurement problem. A quantum particle can exist in a blur of multiple possibilities, a superposition of states, like an electron spinning both clockwise and counterclockwise at the same time. Yet the moment we observe it, this fuzzy cloud of potential collapses into a single, definite reality. The electron chooses one direction. This sudden transition from the possible to the actual is the central enigma. It forces us to ask what truly constitutes a measurement. Is it the act of a conscious mind observing the result? Or is it simply any interaction with the larger environment? The great debates between Niels Bohr and Albert Einstein grappled with this very issue. Einstein refused to believe the moon existed only when he looked at it, arguing for a reality independent of observation. Bohr, however, suggested that at the quantum level, unmeasured phenomena do not possess definite properties. The physicist John von Neumann followed this logic to a startling conclusion. He proposed that the entire chain of measurement, from the particle to the laboratory equipment, could be described by quantum mechanics, meaning it all exists in a superposition. The collapse into a single outcome, he suggested, might require the final step, a conscious observation. This idea that consciousness itself might collapse the wave function is deeply controversial, yet it raises a staggering cosmological question. If the universe was once a single, incredibly dense quantum system, what act of observation caused it to collapse into the specific reality we see around us? Some interpretations desperately try to avoid this role for consciousness. The many worlds theory proposes that the wave function never collapses. Instead, at every quantum decision, the entire universe splits, branching into a multitude of parallel realities. In one world, you see the electron spin up. In another, an identical version of you sees it spin down. every possible outcome happens somewhere in an ever-branching multiverse. Other theories, like objective collapse models, suggest that superposition has a natural limit, collapsing spontaneously when a system becomes too large or massive, without any need for an observer. How does this relate to the fabric of space-time? If a quantum particle's position is indefinite until measured, then the very geometry of space-time, which is shaped by the mass and energy of particles, must also be indefinite. A single heavy particle in a superposition of two locations would, according to general relativity, create two simultaneous gravitational fields, warping space-time in two different ways at once. This implies that space-time events themselves, the when and where of the cosmos, might not be fixed until a measurement of some kind occurs. The universe's own properties, its expansion rate or the distribution of galaxies, could be the result of a cosmic scale observation. So we are left with a deeply personal and philosophical dilemma. Does the solid ground beneath your feet exist independently, a stage set before you arrived? Or is your act of perception, your simple awareness, a fundamental part of bringing that reality into being? The measurement problem suggests we are not just passive spectators on the cosmic stage, but active participants in its creation, entangled in the very reality we seek to understand. Our galactic neighborhood holds a secret that defies everything we can see. Spiral galaxies like our own Milky Way spin so rapidly that the stars on their outer arms should be flung off into the void, like a carnival ride that has spun out of control. They are not. Something invisible, a cosmic glue, holds them together. This is the dark matter mystery, and its solution may be woven into the quantum fabric itself. Astronomer Vera Rubin's meticulous observations of galaxy rotation in the 1970s provided the undeniable evidence. The visible stars and gas simply do not provide enough gravitational pull to explain the speeds. There must be a vast, unseen halo of matter surrounding every galaxy, a shadow skeleton that gives the cosmos its structure. We call it dark matter because it does not emit, absorb, or reflect light. It interacts with our world through gravity alone, a ghostly presence that outweighs all visible matter by a factor of 5 to 1. For decades, physicists have searched for its particle identity. The leading candidates come straight from the quantum playbook, WIMP, or weakly interacting massive particles and actions, elusive particles so light they could be produced in vast numbers in the early universe. These are not ordinary particles. They are quantum entities born from the same primordial chaos that seeded the galaxies. Think of the universe in its first moments, a seething quantum soup. The same fluctuations that gave rise to the seeds of galaxies could have also triggered a phase transition, a cosmic sorting that filled space with a sea of these dark particles. Their gravitational pull then acted as a scaffold, guiding ordinary matter to coalesce into the cosmic web we observe today. But what if dark matter is not just made of quantum stuff, but actually behaves in a uniquely quantum way on a colossal scale? Some theories propose that dark matter could exist as a vast, coherent quantum wave spread throughout a galaxy. Instead of being a swarm of individual particles, it would be a single, diffuse field, its gravitational influence shaping the galaxy from within. This idea connects directly to the geometry of space-time. Einstein taught us that matter tells space-time how to curve. Dark matter, as the dominant form of matter, is the primary architect of that curvature on cosmic scales. Its mysterious nature forces us to ask if it is curving space in a way we do not yet understand. Could it be interacting with hidden dimensions, its gravitational footprint spilling into realms we cannot perceive? Or perhaps dark matter is not a particle at all, but a manifestation of a flaw in our understanding of gravity itself, a quantum correction to Einstein's equations that only becomes apparent on the scale of galaxies. The enigma of dark matter is a direct bridge. It links the frantic quantum genesis of the universe to the majestic rotation of a galaxy, demanding a theory that can speak the language of both the infinitesimally small and the astronomically large. Dark energy is the dominant force in our universe today, yet we hardly understand it at all. This mysterious pressure, which permeates the vacuum of space itself, is causing the cosmic expansion to speed up, not slow down. It was a staggering discovery made by astronomers like Adam Rees, who found that distant supernovae were fainter than expected, a clear sign the universe was stretching apart at an ever-increasing rate. The simplest explanation is Einstein's cosmological constant, a fixed energy woven into the fabric of space-time. But as we saw, this creates the worst theoretical prediction in all of science, a number impossibly large compared to the gentle push we actually observe. So if it is not a simple constant, what is it? Many theorists now suspect dark energy is not a static background. It could be a dynamic quantum field, something that evolves and changes over time, much like the Higgs field that gives particles mass. Imagine this field as a new kind of cosmic weather, one that subtly alters the properties of the quantum fabric itself. For most of cosmic history, this field might have lain dormant, but as the universe expanded and cooled, it could have awakened, its repulsive gravity now taking command of the cosmos. This dynamism holds terrifying implications for the far future. If this dark energy field were to strengthen over time, its repulsive force would grow without bound. Galaxies would first be pulled apart, then star systems, then planets. In a final, apocalyptic end known as the Big Rip, the fabric of space-time itself would be torn asunder. The bonds between atoms would be overcome, and the very threads of reality would be shredded. This is not science fiction, but a plausible, if extreme, outcome based on the potential behavior of this quantum field. Yet, observations reveal another deep puzzle. Dark energy is incredibly uniform, exerting the same gentle pressure in the void between galaxies as it does within our solar system. This smoothness is difficult to explain if it is a dynamic field, which would typically have fluctuations and variations. Its uniformity suggests a profound connection to the vacuum itself, a fundamental property of space-time that is the same everywhere. Why is the energy of the vacuum so exquisitely balanced, so perfectly tuned to allow for our existence? This question brings us full circle, forcing us back to the cosmological constant problem and the deepest layer of the quantum fabric. Perhaps dark energy is not a force at all, but a signature of how quantum information is stored on the cosmic horizon, a holographic effect emerging from the universe's underlying code. The true nature of this dominant force remains the greatest unsolved mystery in cosmology, a silent, invisible engine driving the fate of everything. This cosmic foam of universes could be the ultimate expression of the quantum fabric. Our entire cosmos, with its hundreds of billions of galaxies, might be just one fragile bubble in an infinite, frothing sea of other universes. This is the Multiverse Hypothesis, a staggering idea that redefines the very meaning of reality. It emerges naturally from our most powerful theories, like cosmic inflation and string theory. The same quantum fluctuations that seeded our galaxies could have, on a grander scale, triggered the birth of entirely separate cosmic domains, each with its own unique physical laws. In some, gravity might be crushing. In others, electromagnetism could be too weak to form atoms. Our universe is not special, just habitable. We find ourselves in one of the rare bubbles where the numbers line up perfectly for stars, planets, and life to exist. This anthropic reasoning offers a controversial but powerful answer to the puzzle of fine-tuning. Why is the cosmological constant so small? Because in the vast majority of universes, it is not, and those universes remain sterile and empty, with no one to ask the question. Physicists like Max Tegmark have structured this dizzying concept into levels. The first level is simply a consequence of eternal inflation, where our observable universe is just one patch in an infinitely large, varied cosmos. The second level introduces different bubbles with genuinely different physical constants, born from quantum tunneling events. The most profound levels suggest that every possible mathematical structure might physically exist somewhere. This expansive view directly challenges our place in the cosmos. Does the quantum fabric of space-time extend its threads across all these realities, weaving a meta-structure that connects them? Or is each universe an isolated island, forever sealed off from the others? The most pressing criticism is one of testability. If we can never interact with or observe these other universes, is the multiverse a scientific theory or merely a philosophical speculation? Some researchers search for the scars of ancient collisions on the cosmic microwave background, a bruise left by a neighboring bubble universe bumping into our own in the distant past. Others look for subtle patterns in the distribution of galaxies that might hint at a pre-inflationary geometry. The multiverse hypothesis forces us to confront the limits of science itself. It suggests that the ultimate nature of reality may be a vast, unobservable tapestry, most of which is forever hidden from our view. Deep within the fabric of everything, beyond the reach of any microscope, lies a final frontier. This is the Planck scale, a realm of such incomprehensible smallness that our very notions of space and time dissolve into nonsense. The Planck length is about 10 to the negative 35th meters. To call this small is an understatement. If you were to magnify a single atom to the size of the observable universe, the Planck length would be roughly the height of a single tree. Time at this scale is just as alien. The Planck time, the interval it would take light to cross that tiny length, is 10 to the negative 43rd seconds. An event lasting this long is not a moment in time, it is a fundamental tick of the cosmic clock. The physicist Max Planck first identified these units, realizing they represented a natural limit, a scale where the gravitational force becomes as potent as the other fundamental forces. At this threshold, the smooth, geometric stage of Einstein's relativity and the fuzzy, probabilistic world of quantum mechanics collide with equal strength. Our current theories simply shatter. They cannot describe a reality where space-time is both a curved geometric object and a seething quantum foam. This is the central mystery of quantum gravity. To understand the universe in its first moments, or the true heart of a black hole, we must find the laws that govern this hidden domain. What would we see if we could peer down to the Planck scale? John Wheeler's vision of quantum foam becomes a literal landscape. Space-time would not be smooth and continuous. It would be a churning, probabilistic froth. The geometry of the universe would fluctuate wildly, with tiny wormholes and tunnels forming and vanishing in an endless, chaotic dance. Virtual black holes, microscopic regions of intense gravity, would blink in and out of existence, a constant storm at the foundation of reality. At this level, the universe might be pixelated. Just as a digital photograph is made of individual dots, the cosmos could be woven from discrete, indivisible units of space and time. The smooth continuum we experience would be an emergent illusion, a collective effect of countless quantum grains. Why can we not simply build a machine to see this? The energy required to probe the Planck scale is beyond colossal. It is more than a quadrillion times greater than what our most powerful particle collider can achieve. The universe itself has erected a fundamental barrier to direct observation, a veil over its most intimate secrets. This forces physicists to become cosmic detectives, searching for indirect clues. They scrutinize the ancient light of the cosmic microwave background for subtle imprints left by primordial quantum foam. They analyze the light from distant gamma-ray bursts, looking for tiny delays in the arrival of high-energy photons, a potential sign that they are stumbling over the granular texture of space-time on their billion-year journeys. The quest to understand the Planck scale is the ultimate hunt. It is a search for the atoms of space and time themselves, the final pieces needed to complete our picture of reality. A single equation attempts to erase time from the cosmos. The Wheeler-DeWitt equation, born from the minds of John Wheeler and Bryce DeWitt, is the stark mathematical result of forcing Einstein's gravity into the quantum mold. It describes the entire universe as a static wave function, a single, timeless object. In this breathtakingly simple formula, the variable for time simply vanishes. The universe, according to this view, does not evolve through time. It just is a frozen block containing every event from the Big Bang to the distant future, all equally real and present. It is as if the entire cosmic film exists at once, and our feeling of moving through it is a profound illusion. This timeless picture is deeply unsettling, even to its creators. It highlights the core difficulty of quantizing gravity, forcing us to ask what time actually is. If it is not a fundamental ingredient of the universe, then where does our powerful, unshakable experience of it come from? Physicists like Carlo Rovelli offer a compelling alternative known as relational time. He suggests that time does not exist in isolation. Instead, it emerges from the relationships between events. Think of it like this: a clock does not measure some abstract universal flow. It measures a correlation. The number of times a pendulum swings correlates with the number of times the Earth rotates. Time is the story we tell about these changing relationships. Nothing in the universe happens in time, things just happen, and our perception of time is the order in which we observe those happenings. This shifts the entire perspective. In quantum cosmology, the wave function of the universe would not describe a single history, but a vast superposition of all possible histories, all existing at once. Our journey from past to present would be just one thread in an infinite, timeless tapestry. What does this mean for your reality? It suggests that the flow of time is not a river carrying you along, but a story your brain constructs from a deeper, more static reality. The urgency you feel, the memory of yesterday, the anticipation of tomorrow, all might be part of a magnificent cognitive illusion, a way for a conscious being to make sense of a timeless cosmos. This profound challenge to our most basic experience forces us to look for a new description, one where change itself is the fundamental ingredient of reality. There is another path to quantizing the cosmos, one that builds reality from the ground up using simple geometric shapes. This approach is called Causal Dynamical Triangulations, and it treats the fabric of space-time not as a smooth sheet, but as a vast collection of tiny, triangular blocks. Developed by physicists like Renate Lal, this model takes the idea of a discrete universe and gives it a specific, dynamic form. Each of these triangular building blocks is a fundamental piece of space-time, and they are glued together in a way that strictly respects the flow of cause and effect. Causality is not an afterthought here. It is the central rule that prevents the quantum foam from becoming a chaotic, pathological mess. Earlier attempts to discretize space-time often resulted in bizarre, crumpled universes with an infinite number of dimensions, nothing like the four-dimensional world we inhabit. But by insisting that every connection between these triangles must follow a clear causal order, the model naturally favors the emergence of a sensible, large-scale reality. The true power of this idea is revealed through massive computer simulations. Researchers begin with a random, jumbled soup of these space-time triangles, a disconnected foam with no discernible structure. Then they let the simulation run, allowing the simple rules of causal connection to guide the assembly. What emerges from this digital genesis is astonishing. The chaotic soup of triangles organizes itself, and a smooth, four-dimensional space-time crystallizes from the noise. It is a universe computing itself into existence from the bottom up. Even more remarkably, these simulations have shown distinct phases, including one where the resulting geometry behaves like our own expanding universe. The entire cosmic stage, with its 3 dimensions of space and 1 of time, seems to be a natural consequence of these simple building blocks obeying causal rules. This suggests a profound possibility. The majestic sweep of general relativity and the bizarre probabilities of quantum mechanics might both be large-scale descriptions of a reality that is, at its heart, a vast computation following elementary geometric laws. Could the force of gravity and the expansion of the cosmos simply be the statistical outcome of countless tiny triangles arranging themselves? This computational perspective offers something incredibly valuable, a tangible way to test theories of quantum gravity. Unlike some ideas that remain purely mathematical, causal dynamical triangulations can be run, tweaked, and observed on a supercomputer. It provides a concrete bridge to other discrete theories, like loop quantum gravity, suggesting that a unified vision of a granular universe is within our grasp. We are witnessing the first glimpses of a new kind of physics, where the universe is not described by equations alone, but is revealed as an emergent story written in the simple, causal connections between a near-infinite number of geometric pieces. The relentless flow of time may be the most persistent illusion of all. At the deepest level of quantum gravity, time itself vanishes from the equations. The Wheeler-DeWitt equation presents a universe frozen in a single, eternal moment, a cosmic photograph where the Big Bang and the distant future exist simultaneously. This is the problem of time, a conceptual chasm that forces us to question the nature of reality itself. How can our vivid experience of past, present, and future emerge from a foundation that is fundamentally timeless? Physicist Julian Barber offers a radical vision he calls Platonia, a landscape of all possible nows. In this view, the universe does not move through time. Instead, our consciousness jumps from one now to a very similar one, creating the sensation of a continuous movie from a series of static frames. Change is not something that happens, but a story we tell about differences between these frames. This timeless perspective reshapes our most dramatic cosmic stories. The Big Bang ceases to be a singular beginning and becomes more like a mountain pass in the landscape of Platonia, a transition from one configuration of the universe to another. Similarly, the interior of a black hole might not be a place where time ends, but a region where our familiar notion of time simply no longer applies, replaced by a different kind of order. Without a universal clock, the very idea of cause and effect comes under threat. If there is no before and after at the fundamental level, how can one event be said to cause another? The answer may lie in emergence. Time, like the concept of temperature, might not be a fundamental ingredient but a collective property that arises from the interactions of countless quantum components. Think of a bustling city. The traffic flow is not a property of any single car, but emerges from their collective motion and interactions. In the same way, the flow of time could emerge from the vast network of quantum entanglements and correlations within the universe. Your experience of reading this sentence is not you moving through time, but a complex correlation between the quantum states of the page, the light, and your brain. This enigma forces us to consider that our most basic intuition about reality is a magnificent trick of perception, a necessary story woven by our minds to navigate a timeless and perhaps far more wondrous cosmos. This single, timeless wave function describes everything from the largest galaxy to the smallest particle. It is the ultimate quantum object, a superposition of every possible state the cosmos could be in. This is the domain of quantum cosmology, where we apply the bizarre rules of the quantum world not to atoms but to the entire universe. Stephen Hawking and James Hartle proposed one of its most elegant visions, the no-boundary proposal. It suggests the universe did not begin with a sharp, infinitely dense singularity, a point where the laws of physics break down. Instead, in the quantum fog of the beginning, there was no boundary, no edge of time. The universe would have rounded off smoothly, like the North Pole on a globe. There is no point south of the South Pole, and in this view, there is no time before the Big Bang. The beginning was a smooth, geometric transition from nothing into something. How does this help explain the world we see? The evolution of this universal wave function provides a stunning answer to one of cosmology's oldest puzzles, the profound uniformity of the cosmic microwave background. Why does the afterglow of the Big Bang look almost exactly the same in every direction? The no-boundary proposal suggests that in its earliest quantum phase, the universe was so small and interconnected that it rapidly smoothed itself out. The wave function overwhelmingly favored configurations that were uniform and regular, setting the stage for the remarkably even cosmos we observe. Another breathtaking possibility is that the universe itself was born from a quantum fluctuation. It could have tunneled into existence from literally nothing, no space, no time, just pure potential. This is not a chaotic explosion from a singularity, but a graceful, probabilistic leap, a quantum genesis. This forces us to confront a staggering implication. If the entire universe is described by a quantum wave function, then it exists in a superposition of all possible histories. Every path not taken in our reality is playing out in another branch of this cosmic probability cloud. The specific history we experience, from the formation of our solar system to your own birth, is just one thread in an immeasurably vast tapestry of what could have been. This directly echoes the measurement problem on the grandest possible scale. If the universe is in a superposition, what measured it to collapse into the single reality we perceive? The answer might be that no collapse is needed, and the many worlds interpretation holds true for the cosmos itself. Our entire universe is just one branch of a greater multiverse, forever splitting and diverging. The wave function of the universe is not just a mathematical abstraction. It is a radical reimagining of our origins. It paints a picture of a cosmos born not from a violent bang, but from a quiet quantum rounding, a timeless emergence where all possibilities were, and perhaps still are, equally real. Gravity might not be a fundamental force of nature at all, but a cosmic side effect. This revolutionary idea, championed by physicist Eric Verland, proposes that gravity is an emergent phenomenon, a consequence of something much more primitive, the drive toward disorder or entropy. We are familiar with entropy in everyday life. An ice cube melts in a warm room, its ordered crystalline structure dissolving into a puddle of disordered water molecules. The system moves toward a state of higher entropy, and we never see the puddle spontaneously refreeze into a perfect cube without outside help. Now, apply this logic to the fabric of space-time itself. Verland's entropic gravity suggests that what we perceive as the gravitational force is actually a statistical tendency, much like the pressure of a gas emerges from the collective jostling of countless atoms. In this view, gravity is not woven into the universe's foundation. It arises from the behavior of microscopic bits of information. Think of a holographic screen, a surface that contains all the information describing a volume of space. When an object like a star approaches this screen, it changes the amount of information stored there. The system naturally resists this change, striving to maximize its entropy, and this resistance manifests as what we feel as a gravitational force. The star is not being pulled by the Earth, it is being pushed by the tendency of information to become more disordered. This perspective elegantly reframes one of the universe's greatest puzzles, dark matter. According to entropic gravity, the anomalous rotations of galaxies which we currently attribute to invisible dark matter might not require any new particles. Instead, the extra gravitational pull could come from the universe's information content itself. As stars orbit far from a galaxy's bright center, the surrounding space contains a vast amount of hidden information. and the entropic response to this information landscape modifies the laws of motion on cosmic scales. The observed rotation curves could be a direct result of this quantum information processing, eliminating the need for a mysterious, invisible substance. Is gravity, then, the universe's way of keeping its books balanced, an illusion generated by the relentless drive toward disorder? This idea forces us to reconsider everything we thought we knew, linking the fall of an apple directly to the thermodynamics of a black hole and suggesting that the deepest layer of reality is not force but information. Falling into a black hole should be a peaceful, if terminal, journey. Einstein's equivalence principle assures you that crossing the event horizon would be an uneventful passage, a smooth glide through invisible geography. But modern physics paints a far more terrifying picture. What if the horizon is not a silent gateway, but a searing wall of fire? This is the black hole firewall paradox, a theoretical crisis that threatens to burn the very foundations of our understanding. Proposed by physicists like Ahmed Al-Murray, the paradox emerges from a desperate attempt to protect a sacred quantum rule, the principle of unitarity, which states that information can never be destroyed. We already know that black holes evaporate over eons via Hawking radiation. To preserve information, the radiation leaking out must be subtly entangled with the radiation that came before it. But here is the devastating catch. For that to work, the new radiation must also be entangled with whatever fell into the black hole long ago. Quantum mechanics forbids this kind of promiscuous entanglement. A particle cannot be maximally entangled with two different systems at once. This is the monogamy of entanglement, and violating it would shatter quantum theory. The firewall proposal makes a brutal choice. It sacrifices the smoothness of space-time to save the purity of information. It suggests that at the event horizon, all these incompatible entanglements are resolved in a cataclysmic release of energy, creating a literal firewall that would incinerate any object attempting to cross. The horizon becomes a violent, singular boundary, not a gentle threshold. This directly contradicts Einstein's core idea, which states that a free-falling observer should feel no special forces at the horizon. So who is right? Does Einstein's smooth space-time survive, or does quantum mechanics demand a cosmic inferno? Experts like Joseph Polchinski fiercely debated this, realizing the paradox exposes a deep flaw in how we stitch relativity to quantum rules. The existence of a firewall would mean that space-time is not fundamentally continuous. Locality, the idea that distant events are separate, would break down at the horizon in a spectacular way. The event horizon would be a place where space itself ends, a cliff of reality where the quantum fabric is torn by its own internal contradictions. This dilemma pushes us toward a profound realization. The smooth, classical stage of general relativity and the entangled, information-preserving world of quantum mechanics cannot peacefully coexist at this boundary. The firewall is a symptom of their divorce. Resolving it may require an even more radical step, perhaps where the familiar concepts of space and time themselves are seen as secondary, emerging only from a deeper layer of quantum connections that we have not yet begun to comprehend. This strange role of observation forces us to confront a deeply personal mystery. Does the very act of seeing the world play a part in creating it? This is the enigma at the heart of the Copenhagen interpretation of quantum mechanics. It suggests that a particle's fuzzy cloud of possibilities only snaps into a single, definite reality at the moment it is measured. But what exactly qualifies as a measurement? Is it the click of a detector, or does it require the final step of a conscious mind becoming aware of the result? The physicist Eugene Wigner took this idea to its logical extreme with his famous friend thought experiment. He imagined a laboratory where his friend performs a quantum measurement on a single particle. To the friend inside the sealed room, the particle state has already collapsed. But to Wigner outside, who has not yet looked, the entire system, including his friend and the particle, remains in a blurred superposition of states. Only when Wigner opens the door and asks for the result does the entire situation resolve into one history. In this view, consciousness itself is the ultimate agent that collapses the wave function. This proposition remains one of the most controversial in all of science. Most physicists today favor interpretations that remove the need for a conscious observer. The many worlds theory, for instance, says the wave function never collapses. Instead, the universe splits, with one version of Wigner hearing one result from his friend and another version hearing a different outcome. Another view, known as quantum decoherence, explains that the moment a quantum system interacts with its environment, it effectively loses its quantum properties, appearing to collapse without any conscious intervention. The air molecules bouncing off a particle are enough to pin it down. Yet, the question will not go away. Modern theories of consciousness, like integrated information theory, propose that consciousness is a fundamental property of matter that arises from certain kinds of complex, integrated systems. Could there be a deep, yet undiscovered, link between this kind of integrated processing and quantum phenomena? The implications stretch to the edge of cosmology. If the entire universe began as a single quantum system, what kind of observation could have possibly collapsed its wave function to give us the specific cosmos we inhabit? This line of thinking blurs the boundary between physics and philosophy, between the outer universe and our inner awareness. It suggests that we are not passive witnesses to a preordained reality, but active participants in its unfolding. The quantum fabric may not be a stage we simply walk onto, but a dynamic tapestry that is woven, in part, by the very act of our perception. The primordial cosmos was a seething quantum foam, a churning ocean of potential. In that first fleeting moment, the universe was so incredibly small that quantum uncertainty was not a minor detail. It was the main event. The same vacuum fluctuations that create virtual particles in empty space today were once the entire content of the infant universe. These were not mere ripples on a calm sea, they were the sea itself. Alan Gough's theory of cosmic inflation gave these quantum jitters cosmic significance. He proposed a period of fantastically rapid expansion, a growth spurt where the universe doubled in size over and over again in a fraction of a second. During this violent stretching, the tiny, random fluctuations in the quantum field were not smoothed out. They were magnified, blown up from the subatomic to the astronomical, frozen into the very fabric of space as slight variations in density. Imagine a perfectly smooth sheet of dough. At a microscopic level, the yeast creates tiny, random bubbles. Now imagine stretching that dough to the size of a continent in an instant. Those tiny bubbles become vast hills and valleys. This is what inflation did to the quantum foam. These primordial hills and valleys became the blueprint for everything to come. The slightly denser regions had a bit more gravitational pull, acting as seeds that gathered more and more matter over billions of years. They grew into the first stars, the great clusters of galaxies, and the immense cosmic web we see today. The proof is etched across the sky. The cosmic microwave background, the afterglow of the Big Bang, is not perfectly uniform. It is mottled with tiny temperature differences, a direct imprint of those density variations from the universe's first moments. Without these quantum fluctuations, the cosmos would be a cold, dark, and utterly featureless void. There would be no clumps of matter, no stars to shine, no planets to form, and no one to wonder about it all. So why did certain fluctuations win out? It was a cosmic lottery, a random draw at the quantum level where the winning numbers dictated the architecture of reality. This profound connection means the grandest structures in existence, from sprawling galactic superclusters to the vast empty voids between them, all trace their lineage back to microscopic randomness. The universe we inhabit is not a perfectly ordered machine, but a magnificent accident, a pattern woven from quantum chaos. A black hole appears to be the simplest object in the universe, defined only by its mass, spin, and charge. It should be a cosmic vacuum, a perfect void. Yet Jacob Bekenstein made a startling proposal that a black hole must possess entropy. Entropy is the measure of disorder, the number of ways a system's internal components can be rearranged without changing its overall appearance. A hot cup of coffee has high entropy, its molecules jostling in countless configurations. A pristine ice crystal has low entropy, its structure rigid and orderly. So what could possibly be disordered inside a black hole, a place from which nothing, not even information, is supposed to escape? Stephen Hawking initially resisted this idea, but his own work on radiation forced him to a stunning conclusion. Bekenstein was right. A black hole's entropy is not just a small number, it is colossal, and it is proportional to the area of its event horizon. The formula is breathtaking in its simplicity. S equals a divided by 4, where the area is measured in tiny squares of the Planck scale. This is not a minor detail. It is a fundamental law that stitches thermodynamics directly onto the fabric of gravity. To grasp the scale, consider a black hole with the mass of our Sun. Its entropy would be a number so vast it exceeds the total entropy of all the stars, planets, and gas in the visible universe. All that potential disorder is not stored in some hidden internal volume. It is encoded on the black hole's two-dimensional surface, the event horizon. Each tiny Planck area on that surface, a patch 100 billion times smaller than a proton, acts as a single bit of information, a fundamental pixel in the cosmic display. This is the Bekenstein-Hawking entropy, a direct message that the universe is keeping its accounts on a boundary. The three-dimensional interior we imagine, with all its possible configurations of matter and energy, is perfectly described by the quantum bits painted on the two-dimensional horizon. This is the holographic principle in its most precise mathematical form. The solidity of the world, the very depth of space, emerges from this vast, flat information network. What does this tell us about the granularity of space? The fact that entropy is proportional to area, not volume, screams that space-time is not a smooth continuum. It is pixelated, woven from finite, indivisible threads. The Bekenstein-Hawking formula is more than an equation, it is a key. It unlocks a vision of reality where information is the fundamental currency, and the force of gravity is the thermodynamic shadow of that information processing, a deep secret written on the surface of a black hole and perhaps on the boundary of our entire cosmos. This stretching of space during inflation creates a profound puzzle. As the universe expanded faster than light, it did not just magnify quantum fluctuations. It stretched the very wavelengths of those fluctuations, pulling them from a subatomic scale to a size larger than the observable cosmos. But what happens when you trace this process backwards to the very beginning? You eventually reach a point where those wavelengths were smaller than the Planck length. This is the Trans-Planckian Problem, a confrontation with a fundamental limit. The Planck scale is the frontier where our current laws of physics break down, where gravity becomes as strong as the other forces and space-time itself becomes a seething quantum foam. Our theories of quantum fields and general relativity simply have no validity here. So when inflation stretches a mode from a scale smaller than the Planck length to a cosmological size, it is essentially pulling a phenomenon from a realm of unknown physics into our observable universe. It is like using a recording device that is only designed for audible sounds to try and capture an ultrasound. The device might still register something, but the output would be distorted, a ghost of the original signal filtered through its own limitations. The core of the problem is this: did the properties of these Trans-Planckian modes, governed by a theory of quantum gravity we do not possess, imprint themselves on the cosmic structures we see today. The concern is that the predictions of inflation for the cosmic microwave background, the blueprint of the universe, might not be as robust as we hope. They could depend sensitively on assumptions about what happens in that unknowable realm. If we tweak the physics at the Planck scale, even in a small way, it could change the predicted pattern of hot and cold spots on the cosmic microwave background. For instance, the distribution of these spots, known as the power spectrum of fluctuations, might show subtle deviations from the standard inflationary prediction. It could have a little more power on very large scales or a specific kind of asymmetry. Finding such a fingerprint in the data would be a monumental discovery. It would be a direct message from the quantum gravity era, a fossil from the first moments of time, telling us how space-time behaved when it was woven from its most fundamental threads. So why care about scales we can never directly probe? Because the universe, in its grand expansion, may have done the probing for us. The Trans-Planckian Problem is not just a technicality. It is a stark reminder that our story of the cosmos is incomplete without the final chapter, the one that unites the quantum world with the force of gravity. The quest for a final theory has led us into a mathematical labyrinth of staggering proportions. String theory, in its ambition to unite all forces, reveals not one unique universe, but a nearly infinite array of possible worlds. This is the landscape of string theory, a vast cosmic catalogue of potential realities. Each entry in this catalogue is defined by its vacuum state, a specific, stable configuration of the theory's fundamental fields. The properties of a vacuum determine the laws of physics that would govern a universe born within it, setting the values of constants like the strength of gravity or the mass of an electron. The source of this incredible diversity lies in the hidden, compactified dimensions string theory requires. The way these extra dimensions curl and twist upon themselves, a process known as compactification, can occur in a mind-boggling number of stable ways. Physicists estimate the total number of these distinct vacuum configurations to be around 10 to the 500. That is a 1 followed by 500 zeros, a number so vast it exceeds the count of atoms in the observable universe. This landscape presents a compelling, if controversial, answer to the puzzle of fine-tuning. Why does our universe possess such exquisitely balanced constants that allow for stars, planets, and life? The Entropic Principle suggests that in a landscape teeming with possibilities, we simply inhabit one of the rare bubbles where the numbers line up correctly. In the overwhelming majority of universes, the conditions would be hostile to any complex structure, leaving them dark and empty. Proponents like Leonard Susskind see this as a powerful new framework, a natural extension of cosmology that embeds our world within a much larger multiverse. Yet this very expansiveness is the core of the criticism. Skeptics like Peter Woit argue that a theory that predicts everything ultimately predicts nothing. If every possible set of physical laws exists somewhere in the landscape, how can we ever test or falsify the theory? It risks becoming a metaphysical speculation rather than an empirical science. The search for experimental support is therefore crucial. One key prediction of many string theory models is supersymmetry, a proposed symmetry between the fundamental particles of matter and the particles that carry forces. Discovering evidence for supersymmetry at particle colliders would not prove string theory correct, but it would demonstrate that nature employs the same kind of mathematical structures, lending significant credibility to the landscape idea. Does the quantum fabric itself vary across these countless vacua? In some universes, space-time might be rigid and classical, while in others, it could be a wildly fluctuating foam. The force of gravity could be strong enough to crush atoms in an instant, or so weak it could barely hold a single planet together. The landscape forces us to expand our vision of reality to its absolute limits, contemplating a cosmos where the very rules of existence are not written in stone, but are merely one possible outcome in an endless sea of quantum potential. A single quantum decision does not resolve into one reality, but instead splits the cosmos in two. This is the startling vision of physicist Hugh Everett, whose many worlds interpretation reimagines the quantum fabric as an endlessly branching tree. In this view, there is no mysterious collapse of the wave function. Every possible outcome of a quantum event actually occurs, but in a newly formed parallel universe. The radioactive atom in Schrödinger's famous box both decays and does not decay. In one branch of reality, the cat lives, and in the other, it dies. Both are equally real, and both histories continue forward from that point, completely separate and unaware of each other. This solves the measurement problem with breathtaking finality by declaring that measurement is just a process where an observer becomes entangled with a quantum system, causing their own reality to divide. Proponents like David Deutsch argue this is the most straightforward and logical interpretation of the quantum math, one that removes the need for a special observer. Yet it raises profound questions of its own. If every possible thing happens, what does probability even mean? In this framework, the probability of an outcome is simply the measure of how many branches contain that result. When you flip a quantum coin, the you who sees heads and the you who sees tails both exist, each convinced their outcome was the one that happened. Your identity becomes a fragmented thing, spread across a multiverse of possibilities. This forces us to consider the very nature of the quantum stage. Is space-time itself constantly diverging, weaving an infinite number of cosmic tapestries from the same set of threads? The fabric of reality would not be a single, continuous sheet, but a frothing, bubbling foam of universes, each a slight variation on the last. This endless branching ties directly into cosmological models, suggesting that the entire universe we see is just one twig on an immeasurably vast tree, and that our sense of a single, linear history is the most intimate and personal of illusions. The equations of quantum gravity exist in a realm of pure mathematics, but the truth must be found in the physical world. How do we test a theory about the fabric of space-time itself? The answer lies in a new generation of cosmic detectives, using the universe's most violent events as their laboratory. Gravitational wave observatories like LIGO and Virgo are not just listening for the echoes of colliding black holes, they are probing the nature of reality. When two black holes spiral into each other, they create ripples in space-time that travel for billions of years. In the final, frantic moments before the merger, the fabric is stretched and squeezed to its absolute limit. Could this extreme environment reveal a subtle signature of quantum gravity? Some theories predict that the intense vibrations of the merging black holes would ring down differently if space-time is granular, like a bell made of a different material. The precise pattern of the gravitational wave signal, its harmonics and decay, could carry the faintest imprint of a discrete reality. Another frontier is the light from the edge of the universe. Gamma-ray bursts are the most powerful explosion since the Big Bang, sending photons across cosmic distances. If space-time has a fundamental grain, a kind of pixelation, it would not be perfectly smooth. High-energy photons, with their shorter wavelengths, would interact with this microscopic texture more than their lower-energy counterparts. They would effectively stumble more often on their long journey. This would cause a tiny but measurable delay in their arrival time. A nanosecond lag after traveling for billions of years would be a monumental discovery, a direct message that space is not a continuous sheet. Even our most precise rulers here on Earth are being used to search for the quantum foam. Extremely sensitive laser interferometers are being built to detect a predicted background of holographic noise. If the three-dimensional world is a projection from a two-dimensional surface, then at the Planck scale, space should have a fundamental jitter or blurriness. This noise would set a limit on the ultimate precision of any measurement, a fundamental fuzziness in the very concept of length. Why is this evidence so maddeningly difficult to capture? The energy required to probe the Planck scale directly is beyond astronomical, more than our entire galaxy could produce. We are like listeners in a quiet room, trying to hear the whisper of a single leaf falling in a hurricane. Yet, this immense challenge is driving a revolution in technology and thought. It forces us to be clever, to use the cosmos itself as our particle accelerator, to read between the lines of gravitational waves and ancient starlight. Each null result, each time we fail to find the expected delay or the predicted noise, tells us something vital. It rules out possibilities and guides theorists toward the correct path. The search for quantum gravity is not just about finding an answer. It is about learning how to ask the question in a way the universe will finally respond to. These quantum discoveries force us to question the very bedrock of our existence. If reality is a tapestry woven from probability and information, what does that say about our own choices and our place within the cosmos? The strange phenomenon of quantum non-locality, where entangled particles communicate instantaneously, directly challenges our classical ideas of cause and effect. Philosopher Tim Maudlin points out that this suggests the universe may not be built on a neat chain of local events, where one thing leads to the next in a predictable sequence. Instead, the deep connections of entanglement imply a reality where influence can bypass the traditional flow of time and space, hinting at a cosmic architecture far more mysterious than a simple cause and effect chain. This leads to a profound debate about free will. In a deterministic universe, every event would be the inevitable result of prior causes, leaving no room for genuine choice. But the inherent randomness of quantum mechanics, the fundamental unpredictability of when a radioactive atom decays or which path a photon takes, seems to inject genuine novelty into the world. Is this quantum randomness the physical basis for our own free will? Or is it merely replacing one form of determinism with another, a cosmic dice roll that still dictates our fate? The answers to these questions are not just abstract puzzles, they ripple directly into our ethical and legal systems, which are built upon the assumption that individuals are responsible for their own actions. Another dizzying possibility arises from the idea that the universe might be computable. If reality can be perfectly simulated by a sufficiently powerful computer, does that mean we are living in a simulation? Or more fundamentally, does it mean that the laws of physics are ultimately a set of algorithms, and the universe is a vast computation happening in real time? This perspective transforms the Big Bang from a cosmic explosion into the start-up of an unimaginably complex quantum computer, and every event since has been a step in its calculation. If space-time and matter emerge from information processing, then the solid world around us is a kind of data structure. This blurs the line between the physical and the mental, leading some to wonder if the universe is, in a very real sense, a mental construct. Could consciousness be not just a product of the brain, but a fundamental property of the cosmos, the very thing that gives rise to reality through observation? These are not new questions, but quantum physics has given them a new and urgent language. The idea of a multiverse, where every possible outcome of every quantum decision actually occurs, can feel deeply unsettling. Does it diminish our significance, knowing that for every triumph in this life, there is another version of you experiencing failure? Or does it expand our sense of being, suggesting that we are part of an infinitely rich tapestry of existence? These are not questions that physics alone can answer, but they demonstrate that the journey to understand the quantum fabric is not just about particles and forces. It is a deeply human quest that forces a dialogue between science and philosophy, between the outer universe and our inner world, challenging us to redefine what it means to be real. The ultimate nature of reality remains a tantalizing puzzle, its final pieces scattered across the frontiers of science. We have journeyed through the quantum foam and the holographic principle, but the path forward now demands new tools and a new kind of thinking. The central challenge is to unify the two great pillars of modern physics, to find a single, coherent theory of quantum gravity that seamlessly weaves the probabilistic quantum world with the geometric fabric of space-time. This is not merely an academic exercise, it is a quest to answer the universe's most fundamental questions. How did everything begin? What happens at the heart of a black hole? Why does our universe have the specific properties that allow us to exist? Competing frameworks like loop quantum gravity and string theory offer wildly different visions. One paints a universe woven from discrete loops, a granular tapestry of space. The other describes a cosmos built from tiny, vibrating strings in a higher dimensional arena. Reconciling these two powerful but seemingly incompatible pictures is one of the great intellectual endeavors of our time. Physicists like Sabine Hossenfelder rightly argue that mathematics alone is not enough. We need empirical data, hard evidence from the cosmos itself, to tell us which path leads to the truth. The next great leap will come from observation, from experiments that can probe the fabric of reality in ways we never thought possible. We are already building new eyes to see this hidden layer. The James Webb Space Telescope peers back to the dawn of the first galaxies, searching for faint imprints of the universe's quantum origins in the ancient light. Meanwhile, next-generation gravitational wave observatories will listen for the faintest whispers of cosmic strings or the echo of the Big Bang itself in the primordial gravitational wave background. These signals could carry direct information from the first moments of time, a message from the quantum gravity era. On Earth, ambitious experiments hunt for the elusive particles of dark matter, while others use ultra-cold atoms to create quantum simulations of space-time itself, building miniature cosmic fabrics in the lab to watch how they evolve. The breakthroughs of the coming decades will not just fill textbooks, they will rewrite them. They may reveal that our universe is one of countless bubbles in a vast multiverse, or that the flow of time is indeed an emergent illusion. They could show us what, if anything, came before the Big Bang. The quantum fabric holds its secrets tightly, but the threads of discovery are finally within our grasp. What profound truth will we pull from the cosmic weave when we finally learn to read its deepest patterns? Our journey through the quantum weave has taken us from the cosmic stage of Einstein to the seething foam at reality's foundation. We have encountered a world where particles whisper to each other across the galaxy, where black holes encode their secrets on two-dimensional surfaces, and where the universe itself may be one bubble in an infinite, frothing multiverse. These are not just abstract ideas, they are profound challenges to our deepest intuitions. The solid ground beneath your feet is a tapestry of probabilities. The relentless flow of time may be a story we tell ourselves. The vast emptiness between stars is alive with invisible connections. This vision of reality is both humbling and exhilarating, revealing a cosmos far more mysterious and interconnected than our everyday senses could ever perceive. Carl Sagan once reflected that somewhere something incredible is waiting to be known. That incredible something is the true nature of existence itself, hidden within the quantum fabric. Let this exploration be a starting point, not an end. Let it inspire your own questions, your own sense of wonder about the cosmos. We would love to hear which mystery captivated you the most. Was it the spooky action of entanglement, the holographic principle, or the timeless wave function of the universe? Share your thoughts in the comments below, and if you are eager to continue unveiling reality's deepest layers with us, be sure to subscribe. Together, we can keep pulling at the threads of the cosmic tapestry, forever discovering the incredible something that waits.